Elizabeth here. In this video, we are going to talk about sets and their most basic and fundamental definitions. The first of which is a set itself. So what is a set? Well, it's just a collection of things. The things that a set contains we call elements. All right? And the way we notate that is we write our set, whatever symbol that we're going to use, equals, then we write our squiggly brackets, and then inside those squiggly brackets we include the elements in that set. All right? However, there are many ways that we can describe a set. The first is like above. It's where we just literally list the elements. This is often good with a finite set. So here, S equals the set that contains the elements A, B, the number 2, and the number sign. There are 4 elements inside that set, and the order that we list them does not matter. Another way we can write a set is in set builder notation. You've probably seen this in algebra or calculus. So here, S equals the set of all x, and then those 2 dots reads such that, and then the rule. X is an even integer. So here, S equals the set of all x such that x is an even integer. We can also list a set just by, or describe a set using words. So here, let S be the set of all odd integers. It's clear what that set contains. If you have an odd integer, it lives inside our set S. Now in math, we have some commonly used and important sets that they have their own symbols, and every mathematician should be familiar with those. And you probably are already familiar with all of them, if not most of them. So for example, the set of all reals, that's our R. The set of all integers is denoted with a Z, and the set of all rationals is with a Q. Notice they have these special lines through them to be clear. The set of all real numbers between A and B, including A and B, is another way that you have seen a set listed. Excellent. All right, we also need to talk about the size of a set, denoted as the cardinality, or not denoted, but defined or called, named, the cardinality is a set. Let's say that again. The cardinality of a set is its size. For a finite set, this means the number of elements in that set, and we will denote it with bars. So here, the size of the set S, or its cardinality, is equal to the number of elements in that set S. So for example, if S equals the set AB, the set containing AB, we see that its size is 3, as it has 3 elements. Those elements are A, B, and the set containing AB. These are some interesting elements. Notice that a set can contain a set itself. That can be one of its elements, as is true in our example above. All right, to describe what it means to be an element of a set, we use kind of a funny looking E. So here, A is an element of S. Uses the notation A with that funny looking E, S. All right. Now, a very important set, the set that contains no elements, is called the empty set and has common notation. It's a circle or a big 0 with a bar through it, a slanted bar. Or you could just write it as 2 squiggly brackets with nothing inside. Both of those are acceptable and commonly used ways to express the empty set. Now, a set is called a subset of another set. So here A is a subset of S if every element in A is also in S. And we write S kind of with a flattened somewhat C S. So that reads A is a subset of S. Not to be mistaken with little a is an element of S as above. So think about it. What the difference between something being an element of a set, so it's one of the things inside, and a subset of S, so a collection of those things inside. Now something that's true of every set S, there are 2 sets that are always subsets. The first is the empty set. The empty set is a subset of S for every set S. That is, every element in the empty set is also in S. That one might not be so intuitive for you, as there's nothing inside of the empty set. We just stated that above. But this is an example of something that's vacuously true. Every element in the empty set is also an S. That is not a not true statement. Therefore, it's true. Another set that's always a subset of a set S is the set itself. It is true that every element in S is also an S. Now, often we will think of proper subsets of S, and those are all the non-empty, non-set itself subsets of S. So the things that we think of as a smaller, non-empty set of S. It's kind of how you want to think about it. All right, so for example, let's say S is the set containing, as before, A, B, the set containing A, B, and A is going to be the set just containing A. We see that A is a subset of S since every element in A is also an S. That's clear, right? What's in A? The element little a. That little element A is also an S, therefore, big A is a subset of S. Now note, little a is an element of S, but not a subset of S, right? It's an element, which means it's one of the things inside of S, but it's not a set itself. Now, the set containing A is not an element of S. It's not one of the things in the list, but the set containing little a is a subset of S. So think about that and look carefully at those differences. However, the set containing AB is an element of our set S, and guess what? It's also a subset of S. Why is that true? Well, look at what S is. It contains three elements. One of those elements is the set itself, and that's why the first piece is true. The set containing AB is an element of S. Now, since A and B are elements of S also, then the set that contains those elements are also in S, right? I'm sorry, the set containing just AB is a subset of S, since every element in the set containing AB is also an S. All right, think about that one. Our last definition we need in this video is the power set of a set. So the set of all subsets of a set S is called the power set of S, and is denoted with a squiggly P, or a cursive P of S. All right, so that denotes the power set of S. It's the set of all subsets of a set S. So for example, if S is just the set containing A, B, and C, so a three-element set, right, the size of S is 3, then the power set would contain the empty set, the set containing A, the set containing B, the set containing C, the set containing AB, AC, BC, and don't forget, the final subset of S is always the set itself. All right, so the size of the power set is 8, or 2 cubed. I wonder if there's a pattern there.